Okay, we're going to check, we're going to prove our calculation for an upcoming science discussion. But this is your calculation. Can you walk us through it?
Yes. So here I want to calculate the force of a given solar sail.
Okay.
So given the area of a solar sail, can we find the force that it generates? And vice versa. If we want a force, how much area do we need?
Okay.
Um,
Okay.
So starting out here, doing some bookkeeping, which is energy of a photon is
Mhm.
h nu.
Okay.
Okay. Momentum of a photon is h over wavelength.
Okay.
Okay. And then this next one, I assumed that the solar sail is not a perfect reflector. So I said, the ratio of photons hitting the solar sail is 0.7.
Okay.
And I just assumed it's not a perfect reflector.
So 30% of the energy 30% of the energy is
guess-
going to get absorbed and 70% is going to be reflected.
Yeah, I guess I'm thinking 70% of the photon count. So for every 100 photons that hit the solar sail, 70 are reflected, 30 are absorbed.
Okay, sure. I mean, I
I don't
think
know
this
what
is a guess, right? Like a.
It's a guess, yeah.
Okay.
I think I heard it from for a glass,
Mhm.
70% is a good transmission rate.
That's true.
So I just pulled that number from there and said reflection, 70% is a good reflection rate. It'll change the numbers slightly, but
Sure. It's a first guess. I think it may actually be
Yeah.
frequency dependent, and this is like for your windshield glass with like ultraviolet light.
Right.
But just so that we know, it's some number. Okay, first, it's a rough calculation, not a problem.
Right.
Okay, continue, please.
And then next thing, this little n is the number of photons incident on a meter squared per second.
Okay.
So like you have a meter square area, how many photons from the sun go through that area per second?
Okay.
Which is a number we can find.
Okay.
And then
So
this next part.
Okay. Oh, I'm just following it. So that's this n is the product, or I guess it's the product of the intensity of the photons coming from the sun at that distance, wherever it is, times the area of the sail. All right, so that's how many you catch. Okay, I like that. And then divided by the energy of the photon. Why did you divide by the energy of the photon here?
So I think what intensity is defined as a watt per area.
Okay.
And then
I see.
So if I multiply a watt per area times an area, I get a watt,
which is an energy per second.
If I then divide by the photon energy, I get a count per time.
Yep, sounds good. Because you're dividing the energy per second, dividing it by the energy per photon. The energies cancel, you get the photon per second.
Yeah.
Okay,
so that would be our little n. Yeah. Then next, because we want to get the force, we use Newton's laws, which is just the second law. Force equals the change in momentum over time.
Yep.
And then we'll approximate it. We'll do it over, instead of doing the derivative, we'll do some...
Integrate over a few seconds, sure.
Yeah. Okay. And then we did some I did some rearranging so that the force is... Okay, I did do rearranging. I just plugged in. So the force will be the opposite of the
opposite direction
change in momentum of the photons divided by time.
Okay.
And then I add them up. Instead of doing the total change in momentum of the photons, I add up all the individual photons.
Yep. Sounds good. I'm with you.
Yeah. And then I drop the minus sign because I don't care anymore.
Yeah, we'll just say that it's negative. Not a problem.
Yeah.
Yep.
Yeah. And then I took number of photons. So it's 1 over time. Okay. Multiplied by this sum, which would be the number of photons per second times the area of the sail.
Okay.
Which gives us the total number of photons incident on the sail.
Okay.
Times the momentum change to the absorbed, which is 1. So that's 30% times the momentum of the photon plus 2 times 70% momentum of the photon. So the first term there is what photon comes in is absorbed. Its change in momentum is just p,
right?
Its original momentum.
Yep.
Whereas the photon that comes in is reflected.
Mm-hmm.
That gets 2 times the momentum change.
I agree with that.
Okay. So, and then n times the area of the sail, we defined n as the number of photons incident on a square meter
Sure.
per time.
Yep.
So n times the area is going to be the total number of photons per time
That is
on that
true.
and on area of the sail.
Yep, this thing from before.
And then, what's going on with my delta t? I think the delta t needs to go away because why does it go away? It goes away.
Well, I would think that you multiply it across to get the change in momentum instead of doing the force.
There's a reason. Okay, I think I may have messed up this step here because. So okay, what is n again? If we go little n is number of photons incident on a meter per second. So n. Okay, and so n times a is the number of photons incident per second.
Okay.
Somehow I think I messed up. I want little n to be a big N.
So I think
So that
so is big N the total number of photons, or is it a number of photons per second still?
Yeah, so I think we want, so right now I've defined a little n as photons per second.
Okay.
But I think I actually want little n to be a big N, which should be, if we go up to the definition of little n, I think we want it to be number of photons incident on a meter squared.
Okay. So in order to do that, you would need to do some time integration.
Well, so I'm saying so that the delta t can turn it into a little n. So can we add a definition of big N?
Okay.
We can, on the left side there.
Yep.
Just so I think
there. Do you want a copy and a little paste, a little capital N?
And then n should be number of photons incident on a meter squared. So it's not a rate, it's just a total.
Number.
I think that's what we want.
We want meter squared on the bottom.
Yeah. So I think it should be, big N should be number of photons incident on a meter squared without the time part.
Okay. So this is no longer a fraction. And this is, I can just do it as a text.
I can't quite see what you're doing, so.
Yeah, it's just a second. Photons per meter squared. I guess I should do it as a fraction. Okay. And I need a new line from. You want a number of photons per meter squared?
Yeah. So I think then in the force equals 1 over time n times a. Down there, yeah, that should be a capital N. That's one line above it.
Here.
Yep. That should be an n times a, big N.
Okay, there's once, and then I follow it down.
Okay, and then I think on, one more line with a big N.
Okay.
And then on the third line, it should just be N, and I think we're back to it.
Little n.
Yeah, like that. Yeah. So I think starting on the line, force equals 1 over delta T, big N times A sail times the delta P of all the photons.
Mm-hmm.
Then the next line is some rearranging of the momentum change of the photons by plugging in reflected for P rho absorbed. And then big N over delta T should be little n. And then we've got it.
Okay, so let's just check that here. So you have rho absorbed, which you said here, the absorbed, rearranging for rho absorbed, you get 1 minus rho reflected. Okay, and then you swap that out here. This rho is 1 minus rho reflected. Yes, this might need a parenthesis. So let's instead put a P there. Because it's rho absorbed times P. We rearrange this for rho absorbed, and then I need another P there.
Yeah.
Okay,
maybe just replace the one with a P.
Exactly.
Mm-hmm.
Right there.
Yeah, which I think is fixed on the next line.
Yeah, because you extract it out from everything.
Yeah.
Yep, looking good.
Okay. So force equals the number of photons per second times the area of the sail times the momentum change.
Yep. I like it. Then you do some pluggy plug.
Yeah. So little n is intensity of sunlight times area of the sail
divided by the energy of the photon. There it is.
Energy of the photon. So that's our photon count per time.
Mm-hmm.
And then multiplied by the change in momentum, which is 1 plus rho reflected times P.
Does this require an area squared? Because little n already has an A sail in it.
I think it does not require a squared. I think I messed up my definitions again. I think...
Okay, let's chase it down.
I think in the first force line, force equals 1 over delta T, big N times A sail, that A should be eliminated. That does make sense. That A should be eliminated.
Agreed. Because if you already have the total number of photons per square meter, if you have it multiplied by the area here, it's no longer per square meter, which would be a pressure, I guess.
Oh, wait.
Wait a minute.
I think... Wait.
Wait a minute. Wait a half minute.
N... this is the... Okay, so big N is number of photons incident per second.
Big N, number of photons per second. Per meter squared?
Okay,
per second?
Sorry. It's the number of photons in some length of time.
Okay.
Incident on a meter.
Okay, squared. Yeah.
So I have to multiply that by the area of the sail.
Okay.
To get
the total number.
The total number of photons incident on the sail over some time period. And then if I divide that by delta T, then I get the number of photons per second. So I think if we change...
Okay, so let's see if I understand what you're... So let's see if I understand what you want. So you want big capital N to be the total number of photons, not a number density, total number.
Yeah, maybe we can simplify this by writing... Let's make it total number of photons.
And do?
Incident on the solar sail over some delta T. But the delta T is...
Agreed.
Is implied in there.
So you want N, the total number of photons. And then little n will be the number density, which would then be comprised by this stuff. It's the number of photons per second per area multiplied by the area divided by the energy per photon, and we now are then at the number of photons per second.
Yeah.
Okay.
So